The integral and p-series test, part 1. Let a sub n be a sequence of finite positive terms that decrease to 0. And let f of x be the continuous equivalent to a sub n. For example, if a sub n is 1 over n, then f of x will be 1 over x. Then the integral from k to infinity of f of x dx and the series from k to infinity of a sub n both converge or both diverge. This is called the integral test. Consider the series n equals 1 to infinity of 1 over n. 1 over n consists of finite positive terms that decrease to 0, so we can use the integral test. Which means let's take a look at the integral from 1 to infinity, not of 1 over n, but of 1 over x dx. And we'll see what happens to the integral. Let's rewrite it first. We'll do some proper notation. No pun intended, because we're dealing with improper integrals. But it's the limit from b to goes to infinity of 1 to b of 1 over x dx. Rewriting our limit one more time, and then finding the antiderivative, natural log of x, from 1 to b. If we plug in the top limit, natural log of infinity, that goes to infinity, minus the natural log of 1 is 0, which of course is infinity. Since our integral goes to infinity, we know that the integral diverges. And then by the integral test, the series diverges also. So how does the integral test work? Let's do just a little bit of theory. Let's look at f of x, which is a function that has finite positive terms decreasing to 0, and where a sub n is the equivalent to f of x. Let's put some values down here. Let's say 1, 2, 3, 4. And I'm going to draw some rectangles. So the height of the first rectangle is f of 1, which would correspond to a sub 1. And then the height of my second rectangle is f of 2, which corresponds to a sub 2, etc. And I could continue doing this, but that's good enough to get the idea. And let's suppose that we know something about the integral from 1 to infinity. In fact, suppose that this integral diverges. That means that if we were to take the integral, the value would go to infinity. So why does the series from 1 to infinity also diverge? Well, let's go back up to our picture. Notice that the height of the rectangles are a1, a2, a3, etc., as we stated, but that the width of each rectangle is 1. that means the area of the first rectangle is a sub 1 times 1, or just a sub 1. And the area of the second rectangle is a sub 2, then a sub 3, etc. Now, of course, the series from 1 to infinity of a sub n is a sub 1 plus a sub 2 plus a sub 3, etc., which is the area of the rectangles. Now, what do you notice about the area of the rectangles? Well, if you take a look at them, the rectangles are above the function, which means that the area of the rectangles is greater than the area given by the integral, which is infinite. Which of course means that our series must be infinite as well. Well, what if the integral converges? So in this example, suppose that we know that our integral converges, which means the sum is finite or less than infinity. And let's fill in our graph again. Get 1, 2, 3, 4. And I'm going to draw some right-hand Riemanns, if you would, like such. Similar idea from above gives us the area of the rectangles are a sub 1, a sub 2, a sub 3, etc. And notice here that the rectangles are less than the integral. That is, they are beneath the integral. Now, that's if I start at n equals 2, because I chose to do some right hand. But since the rectangles have a smaller area than the area given by the integral, and that the integral is finite, that implies that the series from 2 to infinity is finite as well. But we know that a sub 1 is finite, and that a sub 1 plus a series from 2 to infinity is, of course, the series from 1 to infinity. So finite, because a sub 1 is finite, plus another finite, because this series is less than the integral, gives us a finite answer as well, which means our series converges.